This is going to be part 2 to section 4.4 videos, and we're just strictly going into examples now. So I wrote down the fundamental theorem of calculus in green, and it's just the definite integral of f of x dx from a to b is equal to capital F of b minus capital F of a, where capital F is the antiderivative of lowercase f. So again, you have to know your your antiderivative or integration rules from section 4.1. So really all we do is we integrate using the rules, and then we apply this f of b minus f of a part, basically plugging in the bounds, the upper limit of integration into the antiderivative minus the lower limit of integration plugged into the antiderivative. So this video, I'll go through these 5 examples. So I guess I'll go ahead and just get right into it. All right, so again, I just integrate first. And using the integration rules that we know from section 4.1. Then apply the fundamental theorem by just plugging in the upper limit of integration minus the lower limit. So then I basically apply capital F of b minus capital F of a. So what I'm going to do first is I'll ignore the bounds for right now and just focus on integrating 7 minus 3t dt. And then I'll apply the f of b minus f of a. If we're going to integrate this, you can break it up as the integral of 7 dt minus the integral, so I guess plus the integral of negative 3t dt. All right, so I'm going to make this go step by step. So from our rules of integration, one of the rules is that if I integrate k, some constant, it turns into that constant times the variable. So in this case, 7 dt turns into 7t. Another thing I can do is I can factor out the negative 3 and focus on integrating t. Well, t is the same thing as t to the first power. So I integrate using this rule. You add 1 to the exponent and divide by that same thing. So it's 1 over n plus 1, and then x to the n plus 1. So this will be, let me separate it. So this is going to be 7t minus 3 times, and it's t to the 1 plus 1 divided by 1 plus 1. And usually you want to put your constant of integration if we're dealing with an indefinite integral. We don't put this when it's a definite integral. But I'm just seeing what the indefinite integral is. So for the definite integral, we had it to be the bounds are negative 1 to 2. And so we integrated it of 7 minus 3t dt. And we got it to be 7t minus, so that's going to be 3 halves. So that's 1 plus 1 is 2, so minus 3 halves t squared. And since we're dealing with a definite integral, I'm going to ignore the constant of integration, and I'm going to put this antiderivative in brackets like this, and then I'll put the bounds -1 and 2. And now I'm going to apply the f of b minus f of a. So that's going to be equal to the f of b part, this is going to be f of 2 minus capital F of -1. So I plug 2 into the antiderivative, so that's 7 times 2, minus 3 halves times 2 squared. All right, that's the f of 2 part. And then I subtract out, so then I subtract f of -1. So I just plug -1 in for t. Okay, so that's the f of -1 part. And then you just simplify it. All right, so for the simplifying, let's see, so that's so 3 halves, I'm timesing that by 4. So then that's going to be 6. So 14 minus 6. And then minus, and then I have -7. And then -1 squared is +1. But I'm doing +1 times -3 halves is -3 halves. All right, and if you calculate all of that, you get 33 halves. All right, so the arithmetic part I'm leaving to you to do, but that's the answer, is 33 halves when you calculate 14 minus 6, then minus, and then -7 minus 3 halves. All right, so the pattern is I integrate, then apply the f of b minus f of a part. All right, so that's that one. Next one's number 13. All right, so I have 2t minus 1 squared. And right now we haven't dealt with integrating yet something squared like this where you have a function inside of the parentheses. We'll learn in a next section a quicker way that we can do this, but for right now I'm going to have to expand 2t minus 1 squared. And when you expand it, that's going to be 4t squared minus 4t plus 1. All right, so I expanded it like that. And I know I got to integrate each piece. So I'm going to skip some steps and just write down what is the result going to be. So right now, I'll put the result in brackets. The 4t squared, well, it's going to be 4 times, and then I add 1 to the exponent. So it'll be 2 to the t to the 2 plus 1, and then I divide by that same thing. All right, and then for the minus 4t, that's going to be minus 4 times t to the 1 plus 1 divided by 1 plus 1. And then when I integrate 1, that turns into t because that's 1 times t. And I'm going from 0 to 1. All All right, and so integrating 1 dt is technically 1 times t, but I just write it as just t. All right, because that comes from integrating just any constant k dx becomes kx plus c. And you know, for the other ones, I was using the power rule for integration. Those are the rules I'm applying. And I just integrated each piece. So I sort of skipped some steps and went ahead and wrote down what the result is, because I know you have to integrate each piece. And I know for each piece, you can factor out, like for the 4t squared, you factor out 4 and then integrate t squared. Then that becomes t to the 2 plus 1 divided by 2 plus 1. Minus 4t, you factor out the minus 4 and integrate t. So that becomes t to the 1 plus 1 divided by 1 plus 1. And then integrating 1 turns into 1t, which is this t, because of this rule. All right, so I'm going to simplify it a little bit. So I have 4/3 t cubed. 4 divided by 2 is 2, so that's minus 2t squared. And then plus t, and then 0 to 1. Now I do my f of b minus f of a. So plug 1 in. All right, that's f of 1. And then I subtract out, or subtract from that, f of 0. Now notice when you plug 0 in for t, all of the stuff goes away because it all involves the variable t. But I'll just go ahead and write it for now. So anytime my antiderivative has t, or only t involved, anytime you plug 0 in, it becomes 0. So all of this collapses away, so you can sort of just ignore that part and focus on the f of 1. So you have 4/3 minus 2 plus 1. All right, so that's going to be 1/3. All right, so I skipped some steps because at this stage we should already know the integration rules. I basically integrated each piece or each term, and then I factored out the constants and applied the power rule. Again, so I add 1 to the exponent and then divide by that same thing. And then when you integrate 1, that turns into just the variable. In this case, the variable of integration is t. All right, then I simplified it some. Then I applied the fundamental theorem by doing the upper limit of integration with the antiderivative minus the lower limit of integration with the antiderivative. Anytime it involves just 0 and you only have just the variable involved, you can just ignore that because it's going to be 0. All right, so that's that one. The next one's number 15. All right, so I'm going to need to rewrite it because I have x squared in the denominator. And I could rewrite this. So you're going to be integrating from 1 to 2, and then 3 over x squared is 3x to the negative 2. So that way I can use the power rule. And then minus 1 and then dx. So I needed to rewrite it first so that the x is with the 3 in the numerator. So I can apply the power rule. So when I integrate this, it's going to be 3 times the integral of x to the negative 2. But when you integrate x to the negative 2, that becomes x to the negative 2 plus 1. Or you add 1 to it and you divide by that same thing. And then I have minus 1. When you integrate 1, it turns into the variable, in this case, variable is x. So it'll be minus 1 times x, which is just minus x. All right, so now I just simplify it some. So we have, so negative 2 plus 1 is negative 1. So I have 3 divided by negative 1 is negative 3. So I have negative 3 x to the negative 1 minus x, and then 1 to 2. You can change that to negative 3 divided by x minus x. So that you don't have the negative exponent. And then now I'm going to apply the fundamental theorem. So plugging in 2, our upper limit, that's going to be negative 3 halves minus 2. And then I do minus, and then our lower limit's 1, so it'll be negative 3 divided by 1 minus 1. All right, so that's our f of 2 minus f of 1. All right, and when you find all this, this comes out to be 1/2. So there's recurring integration rule I keep using, and it's been the power rule. So we should have this ingrained in our head at this point. And then also when you integrate a constant, it turns into the constant times the variable. In this case, very special cases, when we have 1, that turns into just x. All right, so that pretty much has been the rules I've been applying over and over again for integrating. All right, so u minus 2 divided by the square root of u. Now this is a case where I need to rewrite first so that I can make use of the integration rules. Because right now I can't really apply it yet since I don't have anything in the table that I can do with this kind of format. All right, so rewrite first, integrate, then apply the fundamental theorem. So I know square root of u is u to the 1/2. So this is u minus 2 divided by u to the 1/2. By fractions, I can separate this into 2 fractions, where one of them is u divided by u to the 1/2. And then the other one's minus 2 over u to the 1/2. All right, that's just by rules of adding and subtracting fractions. And then I can simplify u divided by u to the 1/2, because that's going to be u to the 1 minus 1/2 by exponent rules. So that's 1 minus 1/2. And then for the minus 2 over u to the 1/2, I want to bring u up to the numerator. So you can do that by changing it to 2u to the negative 1/2. And I'm doing that so I can use the power rule. So I'm integrating u to the 1/2 minus 2u to the negative 1/2. And then that's where I keep using that same power rule. So u to the 1/2, you add 1, so it's u to the 3/2 plus 1, and then divide by that. And then minus 2 times, and integrate u to the negative 1/2, that's u to the negative 1/2 plus 1. And then divide by that same thing. And then again, I put the brackets because we're dealing with a definite integral. And then attach the bounds. All right, 3/2 plus 1 is 5/2. So that's u to the 5/2 divided by 5/2, which we know that's going to turn into 2/5 because you're multiplying by the reciprocal is the same thing. Then minus 2 times, and then I have negative 1/2 plus 1 is u to the positive 1/2. And then divided by 1/2. So I just change these by multiplying by a reciprocal. So 5/2, that turns into 2/5. And then u to the 5/2. And then I do minus 2, and then times 2 is 4. So it'd be minus 4 u to the 1/2. And then 1 to 4. Let's see. Make sure I did everything right. Okay, so I spotted a mistake. So in my head, I knew when you changed u to the 1/2 plus 1, that turns into 3/2. But here I have the 3/2 plus 1. So this is where I made a mistake. I needed to write that as just 1/2 plus 1. Yeah, so that should have been a half. So we have 3/2 written down. It should have been a half. In my head, already kind of, I guess I went ahead and added it because I knew I did a half plus 1 is 3/2. So those should have been 1/2 to where you do 1/2 plus 1 is 3/2. And that's where the mistake was. So I just need to change this 5/2 to 3/2. All right, so yeah, I make mistakes too. So I'll change this to 3/2. This will be 2/3. All right, that's where the mistake was. Everything else is good. All right, so then I apply the fundamental theorem. And so that's going to be 2/3, 4 raised to the 3/2, minus 4 times 4 to the 1/2, which we know is the square root of 4. Then minus, and then just plugging in 1. Okay, so this was f of 4, and then f of 1. All right, so if you find all this, you'll get the first part to be 8/3, or negative 8/3. That's what this comes out to be, and then minus, and then this part comes out to be negative 10/3. So you're doing -8/3 plus 10/3, which is 2/3. All right, so yeah, sorry about that. That's where I messed up. But the point was that I needed to rewrite u minus 2 over square root of u into a format in which I can use my integration rules. And that just involved writing it as two fractions, just using fraction rules. And well, I changed the square root of u as u to the 1/2. And then I separated into two fractions, simplified each particular term, and to where I have u to the 1/2, then minus 2 to the -1/2, so I can apply that power rule for integration that I've been using. All right, and then I did the fundamental theorem, and you get 2/3. All right, so this next one, this is going to be number 25. This is the last example for this video. It's number 25. And so we're integrating 0 to 5, and it's the absolute value of 2x minus 5, and then dx. All right, so for integrating this, it's going to be a little bit more complicated because we have an absolute value sign. And recall that for absolute value, we have absolute value of u that's equal to two possibilities. It's either u if u is greater than or equal to 0, or it's equal to negative u if u itself is less than 0. So that way it's going to make the absolute value of something stay positive. And in this case, our u is like 2x minus 5. So that using that definition, the absolute value of 2x minus 5 is either 2x minus 5, and then in this case, if u is greater than or equal to 0, that's going to be if 2x minus 5 is greater than or equal to 0. And then negative times 2x minus 5 if 2x minus 5 is less than 0. Well, I can write this so that these two options where I have 2x minus 5 greater than or equal to 0. Well, if I solve for x, that's going to give me x greater than or equal to 5/2. And then this will be x less than 5/2. I'm sorry, not less than or equal to. I guess it wouldn't really matter for integrating because it would be the same. So x less than 5/2. All right, so knowing that, I have x greater than or equal to 5/2 and then x less than 5/2. Well, my integral, the definite integral goes from 0 to 5. We know 5/2 is in between 0 and 5. So we know 0 less than 5/2 is less than 5. So I'm going to have two cases. The case 1 would be between 0 and 5/2. And then case 2 is going to be between 5/2 and 5. All right, and that's based off of my two options. So we could have x less than 5/2 that's going to fall under the first case. And then between 5/2 and 5, that's going to be the x greater than or equal to 5/2 case, using this definition of absolute value. All right, so I thought of, well, what's the absolute value of just u? That's equal to u if u is greater than or equal to 0, or negative u if u is less than 0. In this case, our u is the 2x minus 5. So it's either going to be 2x minus 5 if 2x minus 5 is greater than or equal to 0, or negative times 2x minus 5 if 2x minus 5 is less than 0. Well, I just translated, well, 2x minus 5 greater than or equal to 0 is the same thing as x greater than or equal to 5/2, right? Because you add 5 and divide by 2. And then, so that's the first option, is 2x minus 5 if x is greater than or equal to 5/2. And then negative times 2x minus 5 if x is less than 5/2. And then I looked at my integral. The definite integral, the lower limit of integration is 0, the upper limit of integration is 5. 5/2 is between those two values. And so I'm going to have two cases, right? Because I have these two options, whether it's less than 5/2 or greater than or equal to 5/2. Well, since 5/2 is in between 0 and 5, the first case, between 0 and 5/2, that's going to be where I have the x less than 5/2 case. And then the part where I'm between 5/2 and 5, that's going to be the x greater than or equal to 5/2 case. So depending on which case I'm in, depends on whether I use 2x minus 5 or negative times 2x minus 5. All right, so I'm going to summarize. So I can break the integral from, so this was our definite integral. I have two cases. So the case 1 would be between 0 and 5/2. Well, if I'm between 0 and 5/2, so that means x is less than 5/2 case. I have the negative, so I'm dealing with this, negative times 2x minus 5. That's case 1. And then case 2 is between 5/2 and 5. So then I add the second case to the first case. So it'd be 5/2 to 5. So my the integral for x variable varies between 5/2 and 5. Well, that's going to be the second case because it's going to be more than 5/2, which is the just regular 2x minus 5. All right, and that's for how I would integrate using an absolute value. So I break it up into these two cases. All right, so I got to integrate each one. Now I'll just focus on the first one. So I have 0 to 5/2, and it's the negative times 2x minus 5 dx. Well, you could go ahead and you could either factor out the negative or distribute the negative sign. I'm going to just distribute it. So that's negative 2x plus 5. And then dx, and now I integrate. So when I integrate negative 2x, you factor out the negative 2, and then you integrate x. Well, x is the same thing as x to the first power, so you do x to the 1 plus 1, and then divide it by 1 plus 1. Then when I integrate 5, that's a constant. And we know when you integrate any constant, you just attach the variable to it. So it's going to be plus 5x. All right, and then 0 to 5/2 are my limits of integration. All right, so again, I'll just write the rules. So I applied the power rule. And then for the 5, that was, I guess I think, call it the constant rule, I guess you can call it. So integrating a constant k turns into just kx plus c. So in this case, k was 5. All right, so what does that come out to be? So we have the definite, so we integrated, the antiderivative is this in green. So we do -2 divided by 2, it's -1. So I have -1x squared, or just -x squared. And then plus 5x. And then 0 to 5 halves. All right, so now I'm going to apply the fundamental theorem. So it'll be negative times 5 halves squared. So let me put all of this in parentheses. Plus 5 times 5 halves. All right, that's the f of 5 halves, my upper limit of integration. And then minus f of 0, well, notice when I plug 0 in, it's going to go away because you have just the variable x, but I'll go ahead and write it. So that's going to be negative, and then 0 squared, which is 0, and then plus 5 times 0, which is also 0. Okay, so we know this goes away because that's all 0. All right, so when you find this, so this will be negative times 5 halves squared. 5 halves squared is 25 over 4, so this will be negative 25 over 4, and then plus 25 halves. So that's going to give me 25 over 4. All right, that was the definite integral, the first definite integral. So this was for case 1. In other words, when we integrated 0 to 5 halves of negative, and it was 2x minus 5 dx, that came out to be 25 fourths. All right, now I got to take care of case 2. So we know this part is 25 fourths. Now I handle the second case. And I'll put that, I'm using purple for that. All right, so integrating this, we'll get, so I do 2 times the integral of x, that's x to the 1 plus 1, or just x squared, divided by 1 plus 1, or divided by 2. And then integrating -5, that becomes negative 5x. All right, and so the 2's divide out, so you just have x squared minus 5x. And now I apply the fundamental theorem. So I do 5 squared minus 5 times 5. And then minus, and then 5 halves squared minus 5 times 5 halves. All right, so this was the upper limit f of 5, and then minus the lower limit f 5 halves. Well, we know 5 halves, or sorry, 5 squared is 25, and then minus 25. So we know the first thing goes away to 0. All right, because that 25 minus 25. And then it's going to be equal to, and let's see. So this will be negative times, and then 5 halves squared. That's 25 fourths, and then minus 25 halves. So that's minus times negative 25 fourths. Right, yeah, so that's 25 fourths. All right, that's the second case. So we want to integrate it from 5 halves to 5. 5 or 2x minus 5 dx, that came out to be 25 fourths. Okay, so I believe the other case was the same, right? It gave us 25 fourths also. So this was 25 fourths. So we have 25 fourths plus 25 fourths, which is going to give us 50 over 4, which is 25 halves. So we just add the two together. And our answer is 25 halves. All right, and so in this case, just how our integral is designed from 0 to 5, the domain in which we found for the absolute value just happened to be evenly spaced as far as going from 0 to 5 halves, and then 5 halves to 5. So in that sense, they both definite integrals came out to be the same thing, 25 fourths. All right, I don't think, I would not assume that's going to always be the case, because it would be different if that 5 was like a 6. All right, so that's it for this video. The next video, I'm just going to do more examples, but I'll do some trig examples, but I figured I'll do an absolute value one. And really, it's just using the definition of absolute value and applying it to our problem. And then knowing that since our bounds are 0 to 5, we know 5 halves is in between that. So we have the two cases for the integral. And depending on which case we're in, dictates sort of whether we use 2x minus 5 or negative times 2x minus 5. All right, so that's it for this video.